Hey folks, welcome back to another video. Today we're looking at question 662, maximum width of binary tree. The way we solve this problem is by keeping a track of the index at every given level for the leftmost index, for the leftmost node and the rightmost node. And then once we have both of those indices, I think it's called, indices, okay. We calculate the maximum and return that value. So how do we track an index for a given binary tree, right? So as we all know, when we try to represent a binary tree in like an array format, what we could possibly do is we could go we can do any kind of traversal, right? So it can be in order, pre-order, post-order, but and when we are getting the indices for like for the left node and the right node, the index for a given tree, for a given node, if the index is, let's say I, the left child will have the index I plus 2 multiplied by I plus 1. So 2 multiplied by I, and then the right child will have 2 multiplied by I plus 1. So basically for a given node, if the index that we're looking at is I, the left child will have 2 multiplied by I and 2 multiplied by I plus 1. And this is when we represent it in an array format, right? So we can use these indices to calculate the maximum width that we see between like every single level. So let's get started. So we'll be tracking these using like DFS, like at least that's how I'll be solving the problem. I'm sure you could solve this solution using BFS or any kind of other methods as well. But let's start with DFS, right? So yeah, let's call it like a helper method, right? And it needs a couple of parameters. We obviously need to pass the current node that we're looking at, and then we will need to pass like the current level. So like we start with 0 level. So in this case, we'll start with level 0 right here. And then the current index, let's start with 1, because if we do like 0 multiplied by 2 will just be 0, so it'll be a problem. So let's just start with index 1. And because we have to keep a track of like the leftmost and the rightmost index, let's create 2 array lists for that. And we will be using the indexes as like the levels to store like the leftmost and rightmost. Right, so new array list, right? Yeah, okay, awesome. And then let's have this helper method return an int, and we'll just return the value. Awesome. So let's actually write the helper method right now. So we have the tree node, and then we have the level that we're looking at, and then we have the index, and then we have list of integers, and then let's call it left index, and let's do integer right index, and this is for a given level, right? Awesome. So let's actually like clean this up. Let's see if this is cleaner. Yeah, just so that I don't have to. Okay, let's just minimize this. Okay. Now that we started, let's just finish it up. Okay, cool. Now that we have that, let's check for the base case, right? So what is usually the base case for a tree node? It's basically if the tree node is null. So you just return 0 for this. Awesome. So once we have that, we need to check what level that we're looking at. So if you're actually traversing through a given level for the very first time, how do we know that? We know that by checking the size of the indices, right? So like let's say if left index dot size, if it is equal to the level, actually let's just call this level. What does that mean? That means we have only looked at like the previous levels. We haven't looked at a current level. So we will add left index dot add as like the index that we are passed, right? And we do that for the right as well. So what exactly is happening here? Let's talk about this for a bit, right? So basically, this part of the code, what it's trying to do is that we're checking, hey, like, was this level visited before? Because it's a DFS, it's not necessary that like we'll visit like a given level at the same time. It can, like, all the nodes at the given level can be visited at different times. And the way we figure out if a particular level has been visited or not is to actually check the size, right? So because the levels start with 0, if the size is equal to the level, that means we haven't visited it yet. So that way you'll be saying, hey, you know what? The left index and the right index at this point are both index, because we don't know, because we haven't really visited any of the right nodes yet. This is the first node that we're seeing for a given level, so we'll add that. If the size is not at, like, it's not equal to the level, that means it's possibly more. You just update the right index of the level. So instead of adding it, you set the index for the given level as index. So what exactly are you doing here? So if the size is greater, right, you're saying, okay, we have already visited something on the left, so those indexes have been initialized right here, but since we're visiting something else at the same level after, we have to update the index, as in like we're looking at something on the right, further right, that we've seen before. That's why we're updating the index. And because this is DFS, we'll be always approaching like the left nodes before we approach the right nodes. So that's the reason why we have to update the right node to take the latest index, which will be greater. And once we update that, we recursively call it again, right? So it'll be let's get int left. So this will be helper node.left. So since we're going to the next level, we increment the level by 1. And then the index of the left node, as we spoke before, is 2 multiplied by 1. So it'll be index multiplied by 2. And then what else do we need to pass? Left index and then right index. Awesome. So we do that for the left node. We have to do the same for the right. And since it's DFS, that's the reason why we're calling it on the left first and then on the right. We have node.right. We have level plus 1. The index will be index multiplied by 2 plus 1. Since we so that's the index of the right child, and since this is the right child, it's index multiplied by 2 plus 1. And then we have left index, right? You pass back that list, and then you have right index. You could have possibly made this global as well, but it's up to you. Right. So next, what we need to calculate is actually calculate the max, right? So what if, even though you're calling it like further down, but the nodes are null, right? So maybe like the current level actually has like the maximum value, so you calculate the current as well. So how do you do that? So the current level width would be equal to, well, what will that be equal to? It will be right index, and you get for the level, right index at get level. So basically you're getting the rightmost node, and then you're trying to get what is the index for that, and then you're doing that for the left index dot get level, and then you add 1, because like when you subtract, and then like it only gives you the distance, but you also need to add like account for the node as well. So that gives you the current, right? So once we have all of these values, you need to get the maximum between all of them and just return that. So it would be math dot max. So this will be, so you're basically getting the maximum between all of those three, whether is it the current one or is it the one that we calculated. So it will be is it between left and right. Awesome. That's honestly the entire solution. Now let's try compiling this and see if I made any mistakes. Okay, the first few test cases pass. Everything else passes as well. Awesome. So let's talk about the space and the time complexity. The time complexity of the entire solution is O of n. since we have to go through all of the nodes. But the space complexity of the entire solution is of h, where h is the height of the tree, where you just have to store the indices of the leftmost and the rightmost for every single level. Awesome. So that's the solution. If you have any questions, please let me know in the comments below. Don't forget to subscribe to the channel and like the video. I would really, really appreciate that. It definitely keeps me motivated to make more videos. Thanks so much, and I'll see you folks in the next video. Peace.